CoS, ToS, DSCP. I need some QoS at my trust boundary. Hey! Welcome to Quality of Service Marking. Is that yes? I did sit and think of a jingle to remember this title. Not that it will help you in any way, but when you open the can on Quality of Service Markings, you truly open acronym soups and a whole new fleet of stuff that's in your IP header and frame header that you never knew was there before. So we're going to explore marking, quality of service markings in this nugget, looking at the rest of the story, understanding what all these acronyms mean and how to use them, looking at what a trust boundary is, and then finally, we'll look at the configuration. Well, let's dive right in. A review. Marking is the ability to color or mark in some way the outside of a packet or a frame with information so the devices don't have to do what's called a deep packet inspection. Meaning, using my analogy from the last nugget, it's like shipping a box and putting the address label inside the box. You don't want to do that because every stop along the route will have to open the box up to look inside. It's very time consuming. Instead, you put the label on the outside. And we're doing the same thing here. We can put a label at layer 2 and or put a label at layer 3. So the different devices, I mean, you know, at layer 2, switches operate, and switches will be able to look and prioritize the packets based on the marking in the layer 2 header, and routers operate at layer 3. And so the routers will be able to look at the markings inside of there without looking any further, without actually looking at the application data or port numbers or things like that to try and identify it. It can just look at that marking right on the outside and be much more efficient. That's what it is. Now we get to talk about how it happens. Remember when you first got into networking? You probably went through a course at some point where an instructor or a recording broke down and said, okay, well, the IP protocol is very complex. And I'm just thinking back to a course that I took where you got the PowerPoint slide brought up and it said, well, the IP protocol, has all these fields in the header and the version is this and the IHL header length is this and the type of service is this. And, somewhere about there, your eyes are glossing over going, wow, this is not something you wouldn't teach normally. The IP header information all at once. You would just say, hey, this is the header. All this stuff you'll learn in your career. And you will. But all you care in the beginning about is the source and destination address. And then, as you learn about routing a little more, you're like, oh yeah, time to live. That keeps the packet from looping. Oh, as you learn about, the transport layer protocols, you're like, oh, that's how it picks the transport layer protocol. And you just kind of evolve and learn more as you go. Well, right now I'm going to unfold this type of service byte, which, has been there since the 1970s, but people don't pay much attention to. Same thing in the layer 2 header. We learn about a VLAN tag. And when you first learn about VLANs, you're like, oh yeah, there's this VLAN tag. And you may have seen this breakdown, but all your focus is here. VLAN, VLAN, VLAN. You're learning about VLANs. That's all you need to know. Well, now, come to the left, user priority. That's going to be what we're talking about, to where we're looking at the class of service. That's what this is, class of service bits, 3 bits in the header that will allow you to identify things at layer 2. So, layer 2, we have class of service. Now, I added a couple more here just so you're aware. You don't need to know much about them. But just so you're aware, there's other ways of marking. For instance, class of service is an Ethernet thing. That's where our VLANs land. The DE and EXP are for frame relay and MPLS network, respectively. This is the discard eligible bit, and this is the experimental bits. So depending on the type of network that you're going across, like frame relay, you identify quality of service tags using DE bits. MPLS, you'll use the 3 experimental bits that are in there, but our focus, almost 90% of the time, is going to be all sitting right here at the class of service. Now, first thing I want you to notice here, where are these bits at? They're in the header, in the VLAN header. So your method of transmitting quality of service information relies on you having VLAN tags in your header. If you don't have a VLAN tag, there's no field to put the class of service info. There's no marking that I can add to the packet. We add it in the VLAN header. So when you're thinking about network design, here's your phone right here. It goes to a switch, which goes to another switch, which goes to another switch, and so on and so on. You got to have your trunks all across, and even a trunk here to where the phone can send tagged packets. Actually, I'm already getting into trust boundaries. I'll leave that discussion off. But the point is, we're really prioritizing here. But I mean, think about the switches. Where's our congestion at? Right there. I mean, that's our bottlenecks, where all of the clients plugged into the switch go out that 1 or 2 or 3, whatever bundle you have, ports together. So that's where we really need to have our congestion management. So that's where the markings exist. Now, eventually, your switch infrastructure reaches a router. And that router connects you to probably another router and another router, as you go through the rest of your network. Well, what do routers do with layer 2 information? They destroy it. Every single hop where a router receives a frame, it says, okay, I'm going to strip off the layer 2 info here and add new layer 2 info that helps it reach this next one. So we have to have something that allows it to move beyond the layer 2 network, and that's going to be the IP information. Now, here's something interesting. Class of service uses 3 bits, right? Going back to that little protocol breakdown, it's this guy, 3 bits. So I wrote this little chart over here on the left, right, it's the right, to where we've got the common breakdown of the 3 bits. With 3 bits, you can have up to 8 values, 0 through 7. These are all the breakdown of them. Now, over here is a typical use. Now, I say typical because this is what people normally do, and a lot of times what phones will do by default all by themselves. We normally mark best effort traffic with nothing. I mean, this is like our web surfing, our FTP. And then you start having your categories of data, like my low priority data, high priority data. You move up to class of service 3. We're now into voice signaling. Things like SIP, things like RTCP fall into that category. Then we move up to video, which gets number 4, and then voice, the sacred marking 5. Now, this is the common standard. This is a lot of the defaults. Do you have to do it this way? No, you don't. You can choose whatever standard you want. Matter of fact, I should even preface all of this. Marking is optional. You don't even have to mark your packet if you want to. Every device in the network could open the box that you're shipping, could open the packet, do deep packet inspection, and identify what that traffic is. So marking is mainly an efficiency method so that things just move a lot faster. But that being said, almost everybody does it. Now, what's up with this? What are these? What could possibly be more sacred than voice? Well, that's the reserved ones for your network infrastructure protocols. I'll tell you something that's more sacred than voice. OSPF, EIGRP, even Telnet and SSH and some of those kind of things, to where and I've actually talked to somebody. They were like, well, I really see it's like if it's a hello packet or a voice call breaking up, I'm thinking the hello packet should go. No. Because if you lose enough of those hello packets, your whole network infrastructure collapses. Then it doesn't matter who's being prioritized. The thing is on fire. So, again, it's a recommendation. You can do it, but Cisco says, and almost everybody else in the world says, don't use class of service 6 and 7. That's used for our network infrastructure protocols. So, user assignable, level 5. So, again, breaking it down into the binary, you see all the different bits. Also, I've seen... And I've made this mistake, to where you put video and voice into the same queue. You're like, well, I need priority for my video because maybe we're doing video conferencing. Well, it's far more noticeable if the video gets jittery and the audio is. Oh, I said that backwards. It's far less noticeable if the video is jittery a little bit and the voice is staying steady than it is to have pristine, crystal clear video and your audio is going. Breaking up really quick. So video is always one level below the audio. So these are the typical markings we use. So as the phone is sending packets into the switch, most Cisco phones, and I'll say most IP phones, not just Cisco, all of them, by default will tag the packet with a class of service of 5. Now, let's talk about the trust boundary. What is this? A trust boundary is essentially at what point in the network, it's not a technical concept as in something you configure. It's more of like a logical thought process as to where in the network do you begin to trust these markings. I mean, truth is, you've got a computer, in a lot of cases, connected to an IP phone, connected to a switch, connected to another switch, connected to another switch, and so on and so on as you're going through this infrastructure. Where do you start saying, okay, I trust you? Well, ideally, it's right here. This is the ideal trust boundary, where I do not trust the computer, because that would be like trusting your users. We don't trust any user traffic, because somebody could configure their network card to start sending tag packets that have class of service 7 in the header. They're like, I want some high priority, I want some fast connections. I mean, no, we don't want to trust that. So where we'll put our trust boundary is right here at the phone. That's the ideal place, because the further you move that line this way, let's say your phones can't, or you don't trust your phones, so you move the trust boundary right here. That means, all of these different phones coming in, if I could draw them all right here. You got all these different phones coming in. Now this switch is the first place where you start marking your packets. You strip off any markings that come previously, because this is all considered untrusted. Now at the access switch layer, you've got your ASICs in there. It's all hardware based, so it may be able to keep up with that, and that's okay. Maybe you just don't trust the phones. But the further and further you do that, now as you move up to, maybe this is your distribution layer, which connects to all these access layer switches, which connects to all these different phones. You see, the further and further you move this trust boundary bar further away, the more work this device has to do. He's like, whereas if I have my trust boundary here, he's like packaging one box. If I'm using my shipping analogy, he's saying, okay, I'm marking these individual boxes that I'm sending out. Now this guy, he's saying, okay, I've got to package all the boxes for all these phones. That's a little more load. Now I'm packaging all the boxes for all the access switches and all the phones, coming in here. So the further you move that trust boundary, the more work that device has to do, and it can get bogged down. So ideally, we allow the phones to do the work for us. It's similar to I was where was I? I was teaching a class up in San Diego, was it? I flew in to cover for a guy who his wife was pregnant, just to teach a couple days for him on a voice class. And I got there, and the room was just a mess with cables everywhere, phones. They were making phones ring and all that kind of stuff. And so we reached the end of the week. I was like, oh, that was great, thank you so much. And I was like, bye. And they all left. And just as the last person closed the door, I was like, oh, wait a sec. All these cables, all the phones were all still left there. And I spent the next 3 hours winding all the cable up, wrapping it. Whereas if I could have, I would have said, oh, before you go, please just clean up your desk. Wrap all the cables and all that. And I would have had, 20 people that are able to, wrap all these cables and do all this for me. But instead, I became one person doing it. And that's the same thought process as here. So our goal is to buy IP phones and set our network up to where this is where that trust boundary exists. Wait a sec. This. There we go. This is where it exists, where the phones themselves mark the traffic. So class of service is pretty simple. It's layer 2. The switches can look at it and say, okay, that's a higher priority packet because level 5 is set to be better than level 3 and all that kind of stuff. Now, I just want to take a complete side tangent for just a second, because before we dive into the ToS byte, but let's say you've got CoS marking level 5 and CoS marking level 1 and marking level 3. Which is more valuable? Well, we all look at it and we go, well, level 5. Level 5 is the best. And so you have to say, well, okay, well, why is level 5 the best? Well, because you said it was, Jeremy. Well, hang on. Let me back up. I did say level 5 was the best. However, notice I said on that graphic previously, I said it's typically set to 5. Markings are just numbers. They're just colors. You can mark all day long, and your devices will do nothing different. It's like creating, when you first learn access lists on Cisco, and you create an access list, you're like, wow, I created one. What's it doing? Nothing. Well, how come? Well, because you haven't applied it yet. You have to tell that access it's going to be used for something. Now, these markings right here are just numbers. I could, if I was a maniac, go onto all my devices and say, 5 is terrible. I don't like 5. I want to police 5 to 8,000 bits per second, or 8 kilobits per second. In my network, level 1, level 1 is the bomb. This is my EIGRP and my network traffic, and I'm gonna do that. And so you could do that. It's your marking. It's totally up to you. However, you have to remember we're not talking about just your network. We're talking about ITSPs that you're integrating with and service providers that are out there. And so all of them got together and said, well, you know what? We've got to have some kind of standard, some norm. We can't just have people picking numbers and saying, well, I think one's best, and he's like, I think five's best. So they said, let's do this. Let's release these best practices of what these markings should be. Or you should follow this kind of guide when you design it, but it's totally up to you. So I just want to make sure that it's not like an automagic thing. It's not like, well, if I mark 5, then that thing's golden. And well, it's nothing until we know what to do with it. This is just putting the color on the packet. So now let's look at the ToS byte, the type of service. This has evolved over the years. In the beginning, there was what was known as IP precedence. So hang on, let me go back here. I'm going to jump to this. Notice first off, we have type of service right here in the IP header. This represents the bits. 1, 2, 3, 4, 5, 6, 7, 8. It is 1 byte of information. And with 1 byte from your IP subnetting days, right? That's 8 bits, and that gives you 256 values. Well, when the inventors of TCP/IP, whomever they were back in the 70s, rolled this out, they said, well, you know what? Good grief, how many levels of priority do you need? You don't need 256 levels of priority. So let's create this standard for IP precedence, and that's what they called it, where they said, you know what? We're not going to use all 8 of those bits that are in the header. We don't need 250. They said, let's match CoS. Let's keep it right at 3 right here. And then that way we have 8 values, 8 levels of priority that we can set up on our routed devices. And that worked for decades. I mean, quality of service until voice over IP really came out and changed the world. Quality of service was more of a novelty. It was like, haha, my computer's faster than yours. The IT guys use it to surf the web faster than all the users or something. It wasn't really that necessary, except in select circumstances. But now that we have voice over IP changing the world, they said, whoa, we need more levels of priority than just the 8 provided by these. Now we've got Citrix and we've got SQL and Oracle and some applications that are lower and and we've got video and voice and all these different categories. So how do we make this all work? And a brilliant person came up with DSCP. That stands for Differentiated Services Code Point Markings. Now, they had a big challenge on their hand because they said, well, we live in an IP precedence world. There are literally millions of routers out there that, when they're developing DSCP, that are all IP precedence based. They only look at these 3 bits. So they're thinking, okay, we've got to develop a standard that increases the number of bits that you can use, but at the same time keeps it backwards compatible. So for instance, if I have an upgraded router running DSCP and it sends a packet to the IP precedence router, the IP precedence router will be like, oh, okay, well, I get kind of a relative feel of your priority. And same thing here. If he sends him a packet, then he'll be like, oh, okay, I get you. You're kind of in this class of traffic that's coming through. So they had a real challenge on your hand. And if the reason I tell you that is if you don't know that, you're going to look at DSCP and go, this is crazy. What was somebody thinking? This is, why would they do it this way? And once you realize, oh, it's an evolution, then it makes sense. So DSCP introduced more markings and at the same time kept the backwards compatibility. Here's how it did it. It said, okay, well, we're going to use more than these first 3 bits. We're going to use the first 6 bits for a marking level. Now, you might say, okay, well, scratching my head, 6 bits. How many do I get? Well, 64. Well, whoa, wait a second. Is that enough? Oh yeah. Remember, we're not talking about a marking equals an application. We're talking about a marking equals a class of applications. As in, if you've got more than, I would say, 12 classes of marking in your environment, you've gone overboard. I mean, you've gone too granular. You should be able to say, okay, this application fits into, one of these, I would say at most, 12 is a stretch. At most one of these 12 classes of traffic that are out there. And so what they did was they created, up to 64 levels. But they didn't just say, okay, well, let's go decimal on you and you've got levels 1 through 64. No, they had to keep it backwards compatible with this. So they defined that these left most bits are going to define what's considered the per hop behavior. And these bits, actually, I'm going to do something that might scare you. Right here, define the drop probability. Now, that's not documented. You won't be able to go out somewhere and find, oh, well, the line is right there on the drop. But what the standard for DSCP says is that one's always 0. So it's kind of like, well, might as well lop that bit off then, because we never change that one, although those 3 bits are considered part of the drop probability. So here's the best way I can describe it. This on the left is the major class. This on the right is a minor class. Now, when I'm thinking of that, the picture that comes to my mind is boxing. You know, you've got your featherweight, which are the really skinny guys like me, dancing around the ring super fast and just lightning fast guys. But you take one of those featherweight guys, maybe they, the featherweight would have a per hop behavior of 001. And then, you have the minor class. So let's say, my analogy is getting scrambled too soon. Hang on. So you've got the featherweight, you've got kind of the lightweight, then the middle class, then, of course, the one everybody watches on TV, the heavyweight division, and you see all the huge boxers coming out taking each other down. Now, so you've got those divisions, and they keep them separate. They say, okay, well, the featherweight is not going to fight the heavyweight. It just doesn't make sense. So what you've got is inside of there the minor class. So let's say you have a featherweight, class 1, and then over here you've got the drop probability. This is kind of like your subclass. So remember, taking the boxing analogy back to routing, we have to figure out which packets are more valuable than another. So we have to say, okay, we've got the major class that says, okay, if I've got a featherweight versus a heavyweight, there's no competition. The heavyweight's going to win, and the featherweight is going to get dropped if there's congestion on the network. But if I have multiple featherweights, then I go over to this minor class, or what is technically called the drop probability, to say, well, it looks like we're tied on the major class. Let's figure out who gets dropped based on this drop probability. Here, I think we're ready to move to this. This will help me explain it a little more as it relates to DSCP instead of the fighter. So instead of saying lightweight and featherweight and heavyweight and all those kind of things, DSCP breaks it into different classes of traffic. Notice we've got the per hop behavior, again, those first 3 bits up here, which is the major decider. Again, it doesn't even look at the drop probability if you've got different major classes. So instead of featherweight, they say assured forwarding 1. Instead of lightweight, they might say assured forwarding 2. And as you go up, you see assured forwarding 3, 4, and then up here, we have expedited forwarding. Now look at this. If you were to break that into decimal, what would that be? It'd be, let's see, again, our binary is 101. So we treat these independently. Like this is a set of 3 bits, this is a set of 3 bits, this is a set of 2 bits. So we don't put the whole number together until the very end. I'll show you what that looks like. So 101, that'd be 1. There's no 2s. There's a 4. So add those together. That's our 5. So even though we've gone into this more complex and flexible system of DSCP, they've created one quote-unquote class 5, if you will. Remember, class of service level 5 is the highest one you're supposed to assign, and they called that expedited forwarding, level 5. Now you notice, once you get up to here, all these drop preferences options go away because you're not supposed to drop expedited forwarding. There shouldn't be an option. There's not like expedited forwarding level 1, 2, and 3 because it's like this is like your sacred class of traffic or your priority traffic. And when we look at low latency queuing in the next nugget, this will make a lot more sense. So here's where it gets a little bizarre. So let's say we've got a lightweight, or sorry, a featherweight down here. Traffic, assured forwarding 1. That would look like, in binary, is 001 for those 3 bits. And being backwards compatible with IP precedence, it gives you 001 for the IP precedence. It's the same thing, level 1. So if you're again talking from an IP precedence router to DSCP, that's how it makes that leap. Is it says, okay, well you're getting the major class. You won't see all this other stuff because IP precedence doesn't look at all that. It just looks at the left 3most bits. So that's how they made that backwards compatible logic. But right here is where you get a little more options with, okay, well, what if I have multiple levels of assured forwarding 1? Maybe I've got Citrix there versus SQL. well, maybe SQL is a little more valuable than Citrix because SQL tends not to recover if it gets dropped, whereas Citrix kind of will play its role. Well, so you might say, well, I want to put SQL traffic in the low drop category, and I want to put Citrix traffic in the high drop category. Now, this is where it gets a little bizarre. As you come up here, normally, per hop behavior, like as the number increases, you get better, right? Like this is, oh, well, 4 is better than, 5 is better. So it's like you get better. Well, on the drop probability, the higher your number, the worse you are. So it's like this split game. So if you want to take notes, higher is better here and lower is better here. And if you think of the way I'm describing it, if your likeliness to drop, your drop probability is higher, that's a bad thing. Like you're going to be dropped sooner. So here's the point. And again, remember I said this one is always 0. So you're really only using these 2 bits. If I come to a router, let's say it's this router right here, and it gets one packet that is marked 0011100, that's a DSCP marking. Again, break it down. There's your IP precedence 1, high drop probability, and then we haven't talked about those last 2 yet, but this one's always set to 0. So if I get that versus a packet that's 0010100 in the header, again, breaking those down, okay, it goes, okay, well, that's a high drop, and that's a low drop probability. Well, this one is going to get dropped before this one will get dropped. Weird, isn't it? So, again, left side, higher is better. Right side, lower is better. That's the way we want to go. Okay, so let me talk about these 2 bits right here. Flow control. Flow control is a handy thing that is just now starting to really enter the world and be used. I've seen it used once in my life, but it's there. What flow control is designed to do is tell a device to slow down. Brilliant concept, right? So right now, you might say, well, how does a device slow down right now? It gets dropped. So what you see, if you've got a computer sending data, let's say here's our PC sending or receiving data to a server, TCP windowing builds it up like this. Let's say up here is your maximum speed. Like this is physically how far you can go. TCP windowing is like, okay, build. It starts going exponential. It goes, okay, I'm going to keep sending more and more data at once before it hits an acknowledgement until it hits the top. And as soon as TCP hits the top of the list, it cuts its window size by half. So then you come build, back up, bam, cuts its window size by half. Build, back up, bam. So you see these build to the maximum speed and drop. Well, let me show you something. What do you think all this is? That's your computer saying, ouch, I just got hit. Let me back off. Whoa, I'm backing way off on this system, and I'm not going to send data. So this ends up becoming wasted bandwidth that could be used. And so now you start seeing the need for this. With flow control, what can happen is the routed device, as this builds, I need another graph. As it builds up, here's the max speed, the routed device can start sending packets and say, whoa, you're reaching the peak, why don't you slow down? And so you start seeing stuff like this. To where changing these flow control bits is kind of like red light warning. Like, hey, if you keep sending and you keep building at your current speed, I'm going to drop you. And you and I both know that's not going to be good. You're going to drop your window size by half. So why don't you just slow down? And so the computer, if it's configured to adhere to this, can respond and start pulling back and say, oh, okay, let me, as I reach the peak, I'll start slowing down how much I'm increasing my window size until the flow control bits clear. And by the way, these could come in the acknowledgement packets or whatever. When they start clearing, it goes, oh, okay, now it's safe to increase my window size again because now maybe there's more bandwidth available. So that's a pretty powerful concept that hasn't been used in too many places yet. Okay, so it's one thing to watch and see and be like, oh, okay, I got it. I see how DSCP works. And it's totally another to actually say, okay, well, let's do it. Here's your test. Before I put you here, I want to take you to a router so you can see the options that you're given. So I'm back on my UC. We still have from the last night at Facebook Smackdown that we're configuring. But one of the things that you can do, let's go back into our, let's see, where were we? Let's go into our Facebook Smackdown, and we'll go into the class Facebook class map. Now, one of the things that you can do while you're in here is set. Notice set the CoS values. I can say, well, I want to set, and there's all my, I can set the class of service. I can set the MPLS experimental bits, the frame relay discard eligible. I mean, there are all kinds of things that you can set. But I'm going to go into the IP parameters. And by the way, you could do it from right here or here. They just added almost 2 paths to get there. So you can say, I want to set the precedence. Maybe I'm in an old IP precedence router. Notice this is where you have 0, 1, 2, 3, 4. Those are different levels of priority, and they each have their own cool military grade name. So I can back off and I can say, and by the way, this is military. A lot of the military terminology is Department of Defense developed IP. So even if you're not in the military, you can feel like, man, I'm issuing a flash override. So we can also do DSCP. And in here you see the AF11, AF12. Sorry, it's stuck in my head. I got an email yesterday from a guy in Afghanistan taking CBT nuggets. One of our military guys in Afghanistan. He actually included a picture where he was like in the back. It was like a tent that he had this whole networking setup, and he was like, I'm in the middle of a sandy desert doing Cisco networking, and I was like, this is amazing. It's my well, even though I can't be there in person doing like a classroom training, it's like I feel like I'm able to talk to military people on the other side of the world through CBT nuggets. It's just amazing. It's so amazingly wild and wonderful all at the same time. So anyway, you guys are doing amazing stuff out there. Okay, DSCP. So this is how it's categorized. So we see AF1, 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 AF2, AF2. You see how that's worked? But what the Cisco device does, and the way DSCP works, is it puts the drop precedence in decimal as well. So for instance, and the nice thing is it breaks it all down here. If you know what you're doing, you're like, okay, there's my per hop behavior. So this is an IP precedence of 1, or the major class of 1. And then right there's my drop precedence in binary. Now you notice that last digit is always 0. So when we're seeing on here, and so hang on, let me finish my thought here. Here's all the AF. This is what they call class selector, 1, 2, 3, 4. So they're saying if you want to, feel like you're using DSCP, but really mark it the old school way, think of this as like IP precedent. Notice we're not using any of these bits. Then you can use class selector. And then here's expedite. Oh, I forgot to mention one thing on expedited forwarding. I'll mention it in a second. But notice up top, they're like, you know what? If you just want to throw the whole standard out the window and just type in a number, you can do that. Like I said, it's just a marking. It's just recommendations. So it's up to you on what standard you would like to use. So, okay, let's talk about which is better, AF31 or AF33. Okay, well, let's look. We've got right here is the major class. So this would be IP precedence level 3 on a marking if we were to go backwards compatible. But notice we've got a drop precedence next to it. So again, binary, we're looking at 0, 1, 1. So we've got the 6 bits that are DSCP. This one is always 0, so really 5 that we're using. So we've got 0, 1, 1 is the per hop behavior, and then right here the drop precedence, that's 0, 1. Whereas this guy is 0, 1, 1, and then 1, 1 as the drop precedence. So which is better on the drop precedence? Lower is better, higher is worse. So this I'm using all these double negatives here. I'm saying which is better, and I just circled it. So this is better. Assured forwarding 31 beats assured forwarding 33. Okay, how about this one? Assured forwarding 43 versus assured forwarding 31. Well, stop right there. It's kind of like, I don't even need to compare these two. You might go, well, wait a sec. That's a high drop precedence versus a low drop. It doesn't matter. It's kind of like I've got a heavyweight fighter who's at the bottom of his class, but he can sure take down that lightweight that's at the top of his class. Once you go a different major class, don't even compare the drop precedence anymore. Okay, so now I'm thinking certification exam wise, you may see these in terms of binary as well, and they may say, hey, convert assured forwarding 31 to a decimal number. Like you could enter assured forwarding 31 by typing AF31, or you could actually type in the decimal number that's the equivalent of AF31. So let me ask, how would I do that if I was asked to convert assured forwarding 31 to decimal? I would go, okay, 0, 1, 1, 0, 1, but I got to remember, even though I don't use it, the 0 is there. So go back to binary to decimal. We've got 1, 2, 4, 8, 16, 32. right? And we would go, okay, I've got 16 plus 8 plus 2. That equals 26. So if I type in the number 26, it's the same thing as assured forwarding. Did I say? No, assured. I was like, that's not right. Assured forwarding 31 is the same thing if I type in the decimal number 26. So all these are equivalent, if you will. So let's look in the binary. If they just give you a binary number, I would say, okay, right there is my per hop behavior. Right here is my drop precedence. So I'm going to say the per hop behavior is 3. In this case, that's 1 and a 2. Add those together. The drop precedence is also 3, so this would be an AF33. Whereas this one right here, I've got the per hop behavior of, that's 3. And this is a drop precedence of 1. So this would be an AF31 if I was calculating that out. You see how this works? Oh, wait. Which is better? This one. That's the same thing as this, right? So that you see how you can start tweaking and using these together. So let's look at the decimal. What if it says, is 10 or is 14 better? If you haven't seen this before, initially you might be like, I don't know. What do you do? Well, again, just think back to a 6-bit number, a 6-bit value, if you will, and put this on a map of 6 bits. So again, shoot over here. We've got 6 bits. 1, 2, 4, 8, 16, and 32. 6 bits. So if I'm doing 10, I would go, okay, 1, 0, 1, 0, 0, 0. Okay, so I'm looking, and really this is a 1 per hop behavior and a 1 drop precedence, so this is AF11. Oh, so tricky. 14, I go, okay, well, okay, 14, so that'd be 8, 14. Now, wait a sec. No, that's right. 8 and 4 is 12, not 14. So there we go. So add 2, and now we've got our 14. So our value becomes 0, 0, 1, 1, 1, 0. Right? So 10, did I write that out? So 10 is 0, 0, 1, 0, 1, 0. This one's 0, 1. So which is better, 10 or 14? 0, 0, 1, 1, 1, 0. In this case, 10 is. Now that's weird, right? You're like, well, bigger numbers should be better, but if you look, this is really AF1 with a low drop preference. This one is AF1 with a high drop preference. So it's not always reliable to just look at the bigger number and say, oh, well, that one's better. You can't look at it in decimal at all because it'll be deceiving. Let's take a look at 20 and 26. Okay, so we've got 20. 20, I'll just use my existing binary chart, would be 0, 1, 0, 1, 0, 0. That would be 20. And then we've got 26, that'd be 0, 1, so minus 16, that'd be 10, right? So 1, my brain just checked out. Hang on, okay, so 0, 1, that'd be 10, so 8, so 2 is left, right? So 0, 1, 0. Okay, so this is 26. Okay, so which is better on that side? Well, I'm looking here, and on 20, we have an AF2, 1. So that's an, oh, wait, no, that's an AF2, 2. I got to draw my lines in there. I confused myself. AF22, so that would be assured forwarding IP precedence 2 with a drop preference of medium, right in the middle. Whereas 26 is actually AF3. That's the deciding factor right there, with a low drop preference. It's 31. So this is really AF31. This is AF22. Ding, ding, 26 is the winner. So the point in this is you can't look at it in decimal. You have to be able to look at that in binary to figure it out. All right, the last thing I want to do is do a little configuration. But before I did, I was going to come back here because just to throw a zinger in there, let's look at expedited forwarding. Expedited forwarding has no drop preference, right? So it is something marked with a level of 5, which is the highest, or supposed to be the highest user assignable level that you could use. But what is that? What is that? It's a high drop preference, but the way the standard is written is they're like, no. We want you to know that when you get here, that really means no drop preference. Well, why'd you mark it high? I'm sure there was a committee and multiple meetings of, do we make it, I'm sure there was like, well, do we make it 0, 0? And they're like, well, no, because then you can't tell that it's DSCP because it's got the old IP precedence. You're not using any of these bits at all. So they're like, well, do we make it 0, 1? They're like, well, it could be, but then people would think, well, it's 0, 1. Maybe it has a drop. I'm just theorizing. If I was a ghost around a conference room table, what this conversation would sound like. But they finally rolled the dice and flipped a coin, and it was heads. And they said, okay, the drop, the no drop marking will actually be what's high drop, and everything else. Hey, that's kind of fun. So that's expedited forwarding. So let's look at the configuration. But there it is. it's that simple. So what you would do is, as your traffic is coming in, let's get a scenario behind it. Let's say you've got a router or a switch or whatever device is coming in, and you've got a switch and IP phones and all that kind of stuff. And you've gone through. Let's just say you've made it easy on yourself, and you said the entire VLAN of IP phones is going to be priority. Well, what you would do is on the router. Let me exit back out here. Let's kind of start over. Let's do IP access list standard, and I'll just say IP phones ACL. And we'll just say the voice VLAN is, let's do permit 10.5.1.0. So I'm going to say that's my IP phones. Now I'm going to create a class map, and I'll say the class map is going to be voice CM. So I'll say this will match the IP access, it's match the access group IP phones ACL. So I'm going to match those guys. Oh, name. So I'm going to exit out here, and now I'm going to go into policy map. So this is where the marking would happen. I would say, okay, the policy map is going to be called, let's say, mark voice. And I'm going to say for the class voice CM, I'm going to set and that's where I would come in here and say set the DSCP bits to, and right there they have that breakdown that we were just looking at. There's our expedited forwarding at the bottom. That's the one I want to use for my voice, but I could say, okay, set the DSCP to this. But I mean, keep in mind that, and I would apply it, but I want to broaden it a little more. Let's say I've got another one. Let's say I've got IP access list standard, and we'll just say SQL traffic. And I'll say permit maybe the SQL traffic. Now I'm just saying the SQL servers have specific IP addresses or something, right? I made up scenario on the fly. So I'll permit the host 10.59.100.100, which is our SQL server. Exit out there. I create a class map, and we'll say SQL class map match the access group named SQL ACL. Exit back out. Now I would go back into that policy map, which, what was it named? Policy map. Policy map. Well, the name doesn't really make sense anymore, but we'll say for the class SQL CM, I want to set the DSCP to maybe my SQL traffic gets AF 2021. Like a high priority data traffic. So let's do a show policy map now. I just want you to see what we're building here. We have this policy map that says mark voice. The name doesn't make sense now, but we say for the class, we've got the voice class map, which matches the voice VLAN. Set the DSCP marking to expedited forwarding. For the SQL class, set the DSCP marking to assured forwarding, level 21. Now, the last thing to do is to apply it, and I will tell you almost, well, not all the time, but a lot of the time, you will be marking stuff as it comes into the router. The outbound is where you're doing all your other magic. You're policing it, throttling it down or prioritizing it or all that kind of stuff. But as it comes into the router, right here, that's where you want to initially mark it, inbound direction. As it goes out, that's where you want to use all of your queuing, because this is where you usually have congestion, right? So I'm going to go on this router. Let's just say, for grins, this is fast Ethernet 0/1 on, don't even know if I have that interface. Hang on. No, I really meant this is fast Ethernet 0/0. Let's go into fast Ethernet 0/0, and I'll do a service policy input. So as it's coming in the router, be the router, it's coming into you on your interface. I'm going to apply the policy map that I forgot its name, mark voice. right there. Enter. Now we've got it. Now as stuff is coming in, it's going to be marked with those values, which again, I've got to emphasize, mean nothing without stepping it up to what we're going to talk about in the next nugget, which is queuing mechanisms. I would say that by far this nugget of the series represents the most intellectual thought nugget. It wins the intellectual thought award. So if your mind is like, oh, my brain hurts, that's normal, that's okay. It takes some time to get this concept. While I'm rolling it off, keep in mind that it's the beauty of being an instructor is I can take weeks of pain and then put it into a little short nugget and be like, see, it's that easy. But it took a long time for me to get DSCP. So definitely, if you need to go through it a couple times, here's what I want you to do. Here's what we talked about. What I want you to do is go back through and start creating examples. Go onto a router and just do set the DSCP and throw that question mark up there and just make sure that you understand what do all these markings mean. What if I had a 23 versus an 11? What if I had a 40 thrown in there or a 46? What would that mean? And so start throwing some decimals, some assured forwarding, some expedited forwarding. Put it all together and start saying, okay, how does this work? Yeah, and think of it in terms of a boxing match. Who's gonna win when it comes down to it, if I'm following the standard correctly? So practice. It's something that you just need to go through many times to have it soak in. Well, I hope this has been informative for you, and I'd like to thank you for viewing.